Okay, Lorenzo, you have the floor, and please take it away whenever you want.
Yeah, thanks for the organizer. Thanks to the organizer for the invitation. I am Lorenzo Leone. I'm based in Berlin, and this is the title of my talk. It's a question, and I will try to answer to this question in the most meaningful way, I hope. Let me first, though, acknowledge these two very young and brilliant authors. The first one is a PhD student in Harvard, MD, and the second one has been my PhD mate for, we were just me and him back in Boston. So let's try to, encapsulate the problem from a large perspective. So in quantum info, we have many class of states that are very well studied. And the class of state I'm talking about today, which is called doped stabilizer state, is one of these classes. However, many of you don't know about that, but maybe are more familiar with MPSs or free fermionic states, because these two classes, MPS and free fermionic state, comes directly from the many-body perspective, and then quantum information theory just start studying them. For doped stabilizer states, the other way around. They have been basically introduced in the context of quantum information theory, quantum error correction and stuff. And then the question of this work is, do they appear also in the domain of many-body physics? Why is this question, at least from my perspective, interesting? Because, has been during this conference has been many times pointed out that if you have entanglement and classical simulation becomes challenging. Well, that's of course true in the most case, but it's not true in general, because, for example, this class can display very high and trivial entanglement, still can be classically simulated. And I will try to give you all the basic motivation why is this the case. So let me first introduce this class, doped stabilizer states. So since they are doped from states which are called stabilizer states that probably many of you know already, but let me give you the definition anyway. So we are on qubits, the most simple system ever, and we have Pauli matrices, sigma x, sigma y, and sigma z. You can take tensor product of those, as some of us already told you, and you can take a n-qubit quantum state and say, okay, this state is stabilized by a Pauli p if it is an eigenvectors of Pauli p with plus or minus eigenvector. So far, so good. You can go one step further and say, okay, a state is a stabilizer state if there exists n Paulis, which of course need to be commuting between each other, otherwise they cannot stabilize the state simultaneously, and they are algebraically independent. If these two properties holds, then the state is called stabilizer state. And thanks to this property, this theorem holds, the Gottesman theorem. Gottman says that if you, in your quantum computation, only have stabilizer states, so the quantum computation is basically classically simulatable in polynomial time. Another way to phrase it is that, okay, how can I transform stabilizer states to stabilizer states using a class of unitaries, which is called the Clifford group that also Emilio introduced before. And this Clifford group can be defined as, the class of unitaries that transform stabilizer states to stabilizer states. So since this class of states can be easily classically simulable thanks to the Gottesman theorem, which has been introduced 20 years ago, researchers started saying, okay, maybe we can do these Clifford gates, this Clifford circuit that can only create stabilizer states with some non-Clifford gates. One famous one is this P gates with this phase pi/4 here. And then you realize that there's still a classically simulable regime, because the classical simulation is still polynomial in n, but exponential in the number of non-Clifford gates you put in a circuit. And therefore, there's still a classical simulable regime in which you use log n of them. Then you have a quasi-poly regime if you slightly more than log n, and you have the non-classically similar regime in which you use n of them, and other simulation technique may be better. So this class of states, I would say, is interesting in these two regimes in which you have either classical simulation or quasi-poly simulation, and then it becomes pretty much universal. Besides being classically similar or quasi-classically simulable, there are an intriguing property that we'll be using throughout the talk. This is the only technical slide, or maybe non-explained technical slide that you need to trust me on that. These are called the compression theorems, and say the following. So you can define, similarly, with a similar flavor of the definition of stabilizer states, you can say, okay, if there are n minus mu Paulis now that stabilize my state, in the sense that it is an eigenvector with plus or minus eigenvalue, I can say that the state psi has stabilizer nullity nu. I'm just reporting this weird and awful name just because I want to connect with the literature. So that's has been called, this number has been called stabilizer nullity, I don't know why. But so if it contains n minus nu algebraic independent stabilizer boundaries, then why am I introducing those? Because they are very connected to T-dop stabilizer state, because a T-dop stabilizer state has stabilizer nullity basically upper bounded by T. So we can say the stabilizer nullity of this guy is upper bounded by T. Now, what is nice about these stabilizer nullity states is that if a state has stabilizer nullity nu, there always exists a Clifford. You know, remember the trivial class of unitaries that can be simulated easily classically, that is able to concentrate all the non-Clifford part in nu qubits. And therefore, you can call this class of state with stabilizer nullity nu compressible state to remember that there always exists a Clifford that is able to, you know, compress all the non-stabilizer part of the state only on nu qubits. I'm reporting also the compression theorem for unitaries for two reasons. First, because I proved it. Second, because this is a corollary of this one. But we will not use this theorem in this, so you can just forget about it. We just need to remember from now on in the next 20 minutes this formula, just this. Okay, now we have all the technical ingredients to start. And first of all, if I want to find such states in many-body physics, I need to find some Hamiltonians that admit these states as eigenstates. I would say this is really the first step. So, as common or as usual, let's start from the old stabilizer states. Do stabilizer states appear in many-body physics? The answer is yes. And the Hamiltonian are called stabilizer Hamiltonian, which are kind of trivial, but not that trivial, because they are composed, they are sum of Pauli operators that commute with each other. So they are very parent or they are very related to classical Hamiltonian, but not quite. Indeed, these stabilizer Hamiltonian, for example, are ubiquitous kind of many-body physics, or at least many-body physics consider the toric code a lot, or other Hamiltonians of quantum error correcting codes, you know, that encode in their ground space the logical information. So these Hamiltonians are quantum, and the only bad part about them is that all the interaction terms commute with each other. So they are very easily diagonalizable. And the eigenstates of Hamiltonians are stabilizer states. So far, so good. By the way, they can also exhibit topological order according to physics, so they are not that trivial. Are easy tractable, but not that trivial. Now, we start from that and ask, what happens if I perturb a little bit this Hamiltonian here with a perturbation? The perturbation is made out of k Pauli operators. They can be of any size, they can be non-local, they can be whatever, at least. Please.
The additional Pauli operators are also n-body, right?
Well, it's pretty general. You can make it local, you can make it non-local, as you like. I mean, this is a very general statement. Any Pauli operators that commute within this Hamiltonian admit the basis of stabilizer states. Then, if you are in the context of local interaction stuff, you can make it local. But I'm not making this assumption now. But what I'm saying holds for local Hamiltonian as well as non-local Hamiltonian. They will make some assumption. As we have no assumption on this Hamiltonian, I don't want to have any assumption on the perturbation, but you can make it on top after this discussion. So my question is, eigenstates of Hg are stabilizer states. What about the eigenstates of this perturbed Hamiltonian here? Okay, of course, if gamma I are small, the first course of quantum mechanics taught us about perturbation theory. So if gammas are small, we can kind of say that the eigenstates of this new Hamiltonian are close to the eigenstates of Hg. But what about gamma i's are not small? Is there another notion of closeness? The answer is yes, and the answer is yes, and it's also the following. So H, which is a perturbed one, admit an eigenbasis where all the states are stabilized by a group Gj with J, which is a strict subgroup of G. So in this sense, it is not close in the sense of perturbation theory, it is close in an algebraic sense. So they are all stabilized by a group, which is a subgroup of G. And you can also lower bound the dimension of this group with n minus k, where k is the number of these Pauli operators that are disturbing your Hamiltonian. Equivalently, you can say that these have stabilizer nullity nu, which is approximated by k, or they are T-dop stabilizers. So we found them. Then I will skip the proof because I realized that is not that instructive, but I want to just say that strategy, if you want to, at the end of the day, you know, I think the zero cost of quantum mechanics, in order to say, in order to infer properties of the eigenstates, you need to find some commuting operators with your Hamiltonian. So you need to find which group, or at least which Pauli group or subgroup of the Pauli group commute with the whole Hamiltonian. And the easiest way to do it is just to, you know, start from G, the big one that already commute with this, and then, you know, extract some Pauli operator that don't commute with delta H, and you realize that n minus k are sufficient to, you know, commute with the whole Hamiltonian, and then you find again in basis. This is basically the strategy of the proof. But now I want to show you what are the application of these things. Okay, so as I said, I mean, appear in many-body physics, but who cares at the end of the day? At least, can we answer interesting question, like, can we at least probably or maybe diagonalize Hamiltonian? I would say that this is a relevant problem for many body theories, because in general diagonalizing a quantum Hamiltonian is very expensive, right? I mean, you deal with 2 to the n by 2 to the n metrics. So in general, it's a very hard problem. With stabilizer Hamiltonian is easy because every term in the Pauli decomposition commutes, so there are fancy techniques in order to do it polynomially. What about this Hamiltonians? Can we borrow some results from this dop stabilizer Hamiltonian and prove something about their diagonalization? So let me first ask you the question, if I give you, to understand the problem throughout, so if I give you a classical Hamiltonian or a quantum Hamiltonian, what is the first difference in the eigenvectors that you have in mind? Let me answer this question because it's a bit vague. And I would say that if you think about it, a classical Hamiltonian, you can think about it as diagonal in the Z basis. You already know the basis. The basis is a computational basis, right? Or a basis is a computational basis. So you already know the basis of a classical Hamiltonian. However, you cannot say the same of a quantum Hamiltonian. You don't know the eigenbasis in general. The eigenbasis is also very challenging to find. Of course, let me rephrase the previous question of a classical Hamiltonian. I don't know, I'm recorded. You don't know the correspondence between the eigenbasis and the eigenvalue, but you already know this is a computational basis. If you want to phrase it in more computer sciencey way, let's say that you are able to differentiate classical and quantum Hamiltonian because you can sample from the basis of a classical Hamiltonian and just, you know, give bit strings at random. You cannot do the same task for a quantum Hamiltonian because you don't know the eigenvectors. And I'm showing you a pretty pointless result now, but I promise it will be useful for future slides. That also, if I deal with a T-doped Hamiltonian or perturbed Hamiltonian, I know how to sample from the eigenbasis with a time which is only exponential in k, which is independent from the system size, and k is the number of Pauli operators I perturb by Hamiltonian with. And the algorithm is pretty simple, that's why I'm proving it to you. So you have your spectral decomposition of the Hamiltonian. Remember that this, you can choose this basis being of T-doped stabilizer states. But for T-doped stabilizer states, the compression theorem holds, meaning that there is this Saclay first such that every of such double indexed eigenstates can be partitioned in X, a computational basis states on n minus nu qubits times a non-stabilizer states on nu qubits. And this holds for any such an eigenstates here. So you can apply this Clifford on the Hamiltonian, and you will quickly realize that you just block diagonalized the Hamiltonian. Well, if you block diagonalize the Hamiltonian, you now know how to sample from the eigenbasis, right? You just pick a bit string goes on n minus nu bits. You end up with the block of 2 to the k by 2 to the k matrix. Yeah, you brute force diagonalize a block and sample an eigenvectors, and then you return bit string, eigenvectors, and C on top. Okay, it's pretty useless and pretty pointless, but it will be useful for future slides. So at least we know how to sample, but we want to do better. The question is, can we do better? And the answer is no. Computer science teaches us that even if we want to diagonalize a classical Hamiltonian, this problem is NPR. NPR means difficult, means impossible. Or, okay, let's say it means very difficult. Now, classical Hamiltonian are strictly subset of stabilizer Hamiltonians, like the toric code or quantum error correction code Hamiltonian. And then our Hamiltonian are just a strict generalization of stabilizer Hamiltonian that if K grows, then at some point it will reach the whole set of quantum Hamiltonian. For quantum Hamiltonian is even harder, is QMAR, which means even more difficult. And so our hope is not to diagonalize the Hamiltonian, that's hard. Our hope is maybe make some additional assumption and try to find at least the lowest part of the spectrum, or maybe the ground state, because the ground state has a lot of information about our Hamiltonian or the physics described by this Hamiltonian. And the spoiler of the future slide is that the only assumption that we should make is not about the perturbation, which is pretty good, it's just about the original Hamiltonian H0, meaning that if we have an Hamiltonian with such a property, we can study its physics no matter the perturbation we perturb it with, as long as, as enter of this kind of class of perturbation I'm describing. Okay, so you remember when we looked together this pointless task of sampling from eigenvectors, and I promise you it will be useful. It is useful because maybe you realize that the most difficult part of that algorithm, or the most stupid part, let's say, is to sample a bit string X at random, right? Because if I take the right bit string, then I just end up in the right block 2 to the k by 2 to the k of the block diagonalized Hamiltonian. And then if I brute force the diagonalization at 2k by 2 to the k Hamiltonian, I can sort the eigenvector. So the problem just boils down to find the right X. It turns out that, the right X, meaning that the one of the ground state must obey, but the energy with respect to the stabilizer Hamiltonian we're looking at must obey this inequality, which means that the energy cannot be larger than the operator norm of the perturbation. So if you know all the states, the eigenstates of Hg up to this energy, which is just a threshold, you can brute force search in the low energy states of Hg and then sort whatever you find. And this is an algorithm, and this is, I don't know how good is it. I mean, it's really the worst possible algorithm ever, but it works, and at least it works for the ground state. Let's see an example though, because otherwise you just are lost in these matrix inequalities all around. Let's look at maybe the most famous example of stabilizer Hamiltonian, the so-called toric code. In the toric code, you have plaquette and stas operators. These are sol z's, these are sol x, and they turn out to be commuting. And this is an Hamiltonian of the toric code, which is a final quantum error correction code, such that the spectrum and the degeneracies are known. Okay? So we need to find, this is the spectrum, you need to explore all these energy levels from 0 to the operator norm of the Hamiltonian divided by 4. And it turns out that the number of eigenstates, which actually quantifies the cost of your algorithm because you are brute force searching in the low energy spectrum, is n raised to this operator norm. Therefore, if the operator norm is order 1, it means that the search is actually efficient. The brute force is efficient, and so you are able to find the ground states of such Hamiltonians, which I think is pretty nice. Now, as a last application, we know that we can simulate these T-top stabilizer states, and it was the kind of my initial motivation about this work. Can we actually also simulate some physics with these Hamiltonians? It turned out, the answer is yes. For example, we can simulate the quench dynamics, and I heard more than once in this conference that people study actually this quench dynamics. Let me explain it just for completion. For completeness, imagine that you are in, your system is an eigenstate psi naught of the original Hamiltonian H0, so nothing happens. Then suddenly a perturbation kicks in and brings your Hamiltonian from H0 to H0 plus a perturbation delta H, and the system starts evolving with the new Hamiltonian. And you have a state which is time dependent. And you ask, can I simulate this state? The answer is yes. And you can simulate the state with an algorithm which scales exponentially with k, so the number of polyoperators you perturb your Hamiltonian, and independent from t, which also means is fast forwardable, but these are just fancy names, which in quantum info, makes a difference, but not now, I guess. And the reason why it's pretty trivial is always, due to the compression theorem, you always can block diagonalize the Hamiltonian. And the Clifford you use to block diagonalize the Hamiltonian, remember that the subgroup stabilizing the Hamiltonian is also a subgroup of the big group of the only H0. This means that if I apply the same Clifford on the initial state psi naught, it also kind of factorizes the bit string, which is an important times a stabilizer states on a k qubits. And so if I apply any function of the Hamiltonian, or actually this is really quantum mechanics 0, if I apply any function of the Hamiltonian or the Hamiltonian itself, I can, use CC dagger here, and it turns out that the application of the Hamiltonian is just application of a block Hamiltonian on the state sigma here. Therefore, the quantum evolution happens up to a Clifford only on a system of k qubits. That's why I can brute force again, compute that state, and then simulate by algorithms that are out there. I'm not describing those, that are able to simulate states which are stabilizer up to a k qubits, which are not stabilizers. Okay, last slide, maybe the one I like it. Oh no, this is an example. Yeah, this is just to flex because we can simulate 100 qubits. But I mean, the no physics here. It's just, just pointless. I don't know why we're doing this. It's just to show that we can simulate the evolution of plaquette operators with the toric code, with a perturbation, and yeah, so up to 100 qubits, the algorithm works, and this is just a demonstration, but I'm not a many-body theorist, so I don't want to enter the details of what we are doing here. I'm just claiming that if one of you uses this algorithm, can explore very large system sizes. That's the take-home message of this slide. Last slide, maybe the one I like the most, simulating the Gibbs state, which is a very vague concept because we are not able to simulate the Gibbs state even in a classical case. So what am I talking about? But in the quantum case, it's even more difficult to simulate the Gibbs state. Because you usually, the algorithm one would go for is the quantum Monte Carlo, but the quantum Monte Carlo suffers of a sign problem. The sign problem deals with the off-diagonal elements of the Hamiltonian. If you have a real Hamiltonian, the off-diagonal, if they are negative, then this introduces you some overhead, more the negativity of the off-diagonal element, more the overhead. While in the classical case, this is not really the problem. So what I would like to show you is how one can reduce the problem of sampling from the Gibbs state of this quantum Hamiltonian to the problem of sampling a Gibbs state of a classical Hamiltonian, or to reduce to a classical problem. And this I find a bit interesting. And it is always with this compression theorem and this block diagonalizing thing. Because the Gibbs state can be still block diagonalized. Sum of bit string and Gibbs state of the block diagonal Hamiltonians. What does it mean sampling from the Gibbs state? Sampling from the Gibbs state is just a more improved task to the one I introduced before, sampling eigenstates at random. Sampling from the Gibbs state means just that I want to sample eigenstates according to their probability given by the inverse temperature beta and the energy corresponding to the eigenstates. This is the task. But since the state can be block diagonalized, I can sample a bit string, now not at random and according to some meaningful probability. The probability to get a bit string, is to trace out here, which is exactly proportional to the trace of the block diagonal Hamiltonian divided by the total trace. However, the numerator I can evaluate pretty easily, the denominator I cannot evaluate, but with Monte Carlo, you don't need probability, you just need the ratio of probability. And that's the trick. The x changes, but the denominator stays the same. Okay. And then was clear. Nothing, I'm done. And you then simulate I and and I'll put your eigenstates. But I'm done. Here we go. No, still needs flex, but it's useless. 98 qubits. We found this top stabilizer state in many-body physics. We can simulate and diagonalize these Hamiltonians. This opens up two possibilities. One can use this algorithm not as I did, just to flex, but just to explore some perturbative physics of the toric code, for example, to explore the stability of topological order with very, very large system sizes, at least with this perturbation here. one can approach theoretical problems like these Hamiltonians interpolate between trivial stabilizer Hamiltonians to general quantum Hamiltonians. If you force locality, you can maybe answer questions how the recurrence time changes, thermalization properties changes depending on the doping. I don't know. There can be other questions, or for example, one can generalize the non-trivial low energy conjecture to something relating to doping. So very general things. For this, very vague conclusions. Thank you for your attention.
Questions?
If there is a relation between what we're doing and what C is doing, because I would expect that there is a stabilizer evolution. They don't include modulation of the APO or something like that. So in some sense, they would think a modulation of the APS of which they are constant. And in a certain way, you mean that your exact only at the end of kind of stabilizer.
I mean, unfortunately, that's not true because the Clifford generates very high entangles. So this, unfortunately, these are different regime. I mean, MPS and MPO.
Yes, in the operatorial space.
Oh, I see. In the Heisenberg.
Yes.
Huh. I never thought about that, but it would be interesting to see. I mean, I don't know. I mean, my experience when you try to combine MPS and a Clifford, you're always unhappy, but maybe in the Heisenberg picture, there may be some.
So with the range, so if you think about studying equilibration or local observable.
Exactly. This is an example. I mean, as you can see, I'm very, I was very focused on the algorithm part. I want to give a tool. I didn't study anything.
I'm not sure there is a result.
What do you mean?
There is, I mean, it's in equilibrium, I think, even with the toric focus, not so clear.
So you mean if you
Benching, toric,
Yeah. I mean, I'm not a many-body theory, so I don't know the results which are out there, but yeah, I hope that these tools can be useful actually.
There is also a paper so it's to Clifford and then you do one T gate and then you do Clifford again. And you look at the state that you get after some time. And the claim, I think, is that if you look at the entanglement Hamiltonian of that state, it's very much generic. So you get level repulsion.
Yeah.
So it's a chaotic state.
Yeah.
But you can simulate very well this state, or there's something I missed.
Yeah, no, but also there, I mean, in that paper they use in that paper what they use a random state at the beginning, then a Clifford T-gate Clifford. Okay?
It's a product state.
Exactly. But the product state can contain arbitrarily many T-gates up to order n. So at the end, in total, in that kind of states, you have order n T-gates. So you cannot simulate.
I remember the type is like one T gate can give you generic.
Yes, I mean the title of papers can be misleading. I mean we all agree on that. And second, I mean they start from a product state. I know the paper very well. I mean it was my advisor. He taught them about it. So they have random product state. The random product state can contain up to n T-gate, many T-gates, right? So they have one T-gate in the middle, and they like to claim this weird stuff. But we are in this regime.
So what you claim is that paper you have T-gates already in the
Well, yes, because you start from a product state. Actually, they start from a random product state, which contain n T-gates. I mean, with probability 1. So we are in this regime. Cannot be simulated.
So if you have product state, let's say 0, 0, 0, and then 1.
0, 0, 0 does contain n T-gates. It's a random product state, which is a
0, 0, 0 plus 1 T-gate somewhere, then this one is simulatable as you see.
yeah, absolutely, yeah, very efficient. Yes.